Okay, welcome back. In this video, we're going to talk about how chemists determine the mass of atoms. So before we start, I want to make sure you have a few things out and that you're ready. One is a periodic table, and the other one is your workbook with your guided notes open. Chapter 1 guided notes. Okay, where it says mass of atoms. Okay. So if you look at the periodic table, before we get started, I want you to tell me what's the atomic mass of hydrogen? 1.01. Okay, if you look at the periodic table that I gave you, 1.01. What is the atomic mass of helium? 4. What is it for lithium? 6.94. In this video, we're going to show you how chemists come up with that number, why it's a decimal. Okay, why isn't it just a nice whole number? And so you'll be able to do that at the end of this video. So let's get started with your guided notes. Mass of atoms. Okay. Atoms are too small to find the mass in grams. It's not like we can take a single atom over to the electronic balance and find its mass in grams. It's way too small to find it in grams. The unit of mass for an atom is called an atomic mass unit. So an atomic mass unit, it's abbreviated AMU. So again, it's not in grams. Atoms are just way too small to use that unit of measurement. We call them atomic mass units. So what's an atomic mass unit? So 1 AMU is defined as 1/12 the mass of a carbon-12 atom. It's kind of relative to the carbon-12 isotope. 1 AMU is defined as 1/12 the mass of a carbon-12 atom. So an AMU is nearly, but not exactly, equal to 1 proton and 1 neutron. So if you look at this table, a proton and neutron, pretty close to 1 AMU, 1 atomic mass unit. And the mass of an electron, 0.0005. Way less. So when we're talking about the mass of the atom, where's most of the mass coming from? The proton and the neutron. Where is that found? What part of the atom are they found in? It's in the nucleus. So even though that nucleus is very small, that's where most of the mass is found. So we're not even going to consider the electron when determining the atomic mass of an element because they're too small. We could calculate their mass into it, but it wouldn't matter anyway. They're just way too small. Okay, so atomic mass. Let's define that. The atomic mass of an element is the weighted average mass of all the isotopes of that element. So it is the weighted average mass of all the isotopes of that element. Okay. Let's go through this chart right here, this diagram, and hopefully explain it so that makes sense. What's a weighted average of all the isotopes of that element? Okay, get your periodic table and tell me the atomic mass. Some people call it atomic weight. That's something I should say. In your guided notes, make this note. Atomic mass and atomic weight are used interchangeably by chemists. So if you hear atomic mass, it's the same thing as atomic weight. You usually find it at the very bottom of the box on the periodic table. So for chlorine, somebody tell me what the atomic weight of chlorine is. 35.45. Okay, 35.45. Let's see why it's a decimal and why it is this. Okay, chlorine has 2 isotopes. Chlorine 35 and chlorine 37. Okay. Now the weighted average part, then we have to look at the percent abundance of each isotope. What's the percent abundance of chlorine 35? Well, it's about 75.7, so 76%. What's the percent abundance of chlorine 37? It's only 24. Which one's going to factor into this average more? Well, the chlorine 35 is going to factor into more of it because it's more percent abundance. It's a lot more prevalent. So why is this number right here, 35.45, and not 37 like this one? Well, it's closer to the 35 because there's just more of chlorine 35 than there is chlorine 37. Okay. Now, it's not, but say it was this, 1% was chlorine 35. And say 99% of it was chlorine 37. What would the atomic weight of chlorine be? Almost 37, right? It would almost be 37. It would be slightly lower than that because you have some chlorine 35, so it might be 36.9. Okay. So that's where the weighted average comes from. We have to take all the isotopes and it's a weighted, based on its percent abundance. It's a weighted average. Okay, practice problem number 10. It says to calculate the atomic mass of the following element. Okay, here's our element. It's not a real element, it's just X. It's not really found on the periodic table. But it has two isotopes. There's X6 and there's X7. Again, this is its mass number. So how would we find it? Here's how you do that. You're going to take it, so let's do it for X6. Hopefully you're writing this as I go through it, because you're going to have the next practice problem is going to be yours. So for X6, we're going to take its atomic mass in AMU, so that's 6.015, and times it by its percent abundance. Okay? We're going to times it by its percent abundance, but we need it in a decimal form. How do you get that percent to a decimal form? Move it over 2 times. Which way? To the left. Okay, so we move this, to get it out of a percent, we need to move it 2 to the left. So that's going to be 0.0759. Okay, let's do that on your calculator. So 6.015 times 0.0759. Oh, I'm sorry. Okay, so what do you get when you do that? 0.465385. Okay, so if you take 6.015 and times it by 0.0759, you get 0.45. Let's just round that 7. Okay. Now let's do the same thing for X7, this isotope. So we're going to take its mass, which is 7.016, and times it by its percent abundance is going to be, move it over 2 times, 0.9241. Okay. Are you guys getting 6.4834? Okay. Now what you'll do is add those two together. Because we've taken the weighted average now. This and this were the weighted average. Now let's add those two masses together. Are you getting 6.94 AMUs? Okay. So that would be the atomic weight of this element X. 6.94 AMUs. Now let me ask you this. Why is it closer to 7 than it is to 6? Because we had X6 and X7. Why is it closer to its atomic weight closer to 7? Why? Which one had a higher percent abundance? Which one is more prevalent? X7. So when you do the weighted average, that's why it's closer to 7 than it is to 6. And so hopefully you see that. Let's do an actual one from the periodic table. Okay, did we get it right? 6.939. Yeah, we rounded it to 6.94, so we got it right. Okay. Let's do practice problem 11. This one comes from the periodic table. What element are we talking about? Boron. So when you're done, look at boron on the periodic table and see if you got it right. Okay? Let me help you get started. It has two naturally occurring isotopes, boron 10 and boron 11. So what I would do is just put B10, or boron 10. What was its, so its mass was 10.013, and we're going to times it by its percent abundance. How do you change it? Move it 2 decimals to the left, so 0.198, and that will give you something. Okay, for boron 11, we can take its mass, which was 11.009. Again, I'm getting that from these numbers here. Timesing it by its percent abundance would be what? 0.802. Okay? So let's do that multiplication now. For the top one, I'm getting 1.982574. The bottom one, I'm getting 8.829218. If you add those two numbers together, I get 10.811792. Now let's look at boron on your periodic table. I hope that this is its atomic weight. Is it? 10.81 AMUs. So 10.81, if you looked at boron on the periodic table, that's its atomic weight. So anyway, that's why it's not just a nice whole number. It's always going to be a decimal because it's a weighted average of all the isotopes. Take its mass, times it by its percent abundance for each one, and then in the end, you add these two numbers together. Hopefully that helps you see how they get atomic weights on the periodic table. Now, knowing that, you guys can complete a worksheet. In your workbook, it's titled the Atomic Structure Worksheet. There's a few pages to this one. So 1, 2, 3, 4 pages to that worksheet. So hopefully this helps you understand that.